satisfaction through group standards. Okay, so the best way to start any physics talk is by listing some interesting physics problems, and Nature provides us with a host of those. Here's one from condensed matter physics. So typical metals, including those you learn about when you take junior statistical mechanics, especially those that also become superconducting at low temperatures, are governed by something called Fermi liquid theory, whose justification Andre has somewhat reviewed. It's a guess based on the notion of adiabatic continuity. But the basic picture in Fermi liquid theory is that if you have a gas, a fermion, at some finite density, then you fill up single particle fermion states. So you have particles in a box with some momentum, you fill up the higher and higher momentum states in the box until you reach some fermion momentum. And since each momentum can only be occupied by most two fermions, you grow a sphere that's ever larger in momentum space after some k fermi. Now, basic quantum mechanics, in a sort of single particle plus weak interaction picture, together with just the kinematics of the Fermi surface, the states within the Fermi surface are doubly occupied and hence inaccessible as intermediate states, while the states on the surface can pop up a little bit above the Fermi surface and get some extra energy. These two facts together determine roughly a lot of properties of the simplest metals. For instance, the specific heat in the regime where this is the dominant picture should be linear in G. The resistivity should go like T squared based on just Fermi's golden rule, and so forth. And maybe it's a surprise that this works remarkably well for many metals. Now, the fixed point, which comes about when you take this picture and make it into a quantum field theory, that was first done relatively late by Schoenfeld and Bolsinski and others, has a Fermi liquid fixed point, which is in the terminology of the normalization group, an infrared stable fixed point. That's not quite true. There are some marginal perturbations corresponding to the so-called Landau parameters, and in some cases there's one marginally relevant perturbation corresponding to the Cooper channel instability generated by photon exchange. But basically, it's an infrared stable fixed point, and that's what explains its ubiquity in real-world metals. And that presumably is why this picture has had so much success. But a variety of experiments starting in the 1980s and continuing with greater and greater precision until today yield phase diagrams for relatively simple metals that have decidedly non-Fermi liquid behavior. Whatever is governing their behavior above, say, a superconducting dome that's seen in the Cooper rates, it's not this picture, because these exponents come out wrong. Because here's a picture of active data from a couple of years ago in a heavy fermion system. The vertical axis is temperature, the horizontal axis is magnetic field. There's presumably a quantum critical point here. Fermi liquid theory resistivity, and orange is linear resistivity. So there's very convincing evidence now from experiments that there are sort of quantum critical bands in the T versus order parameter, T versus control parameter phase diagram that exhibit this non-Fermi liquid resistivity. So these materials suggest at the broadest level a challenge. They risk string theorists, none of us can even really figure out what this compound is, so the challenge is not to explain this data exactly. But the challenge is there are apparently qualitatively new infrared stable phases of matter, or almost stable phases of matter, that can be classified infrared almost stable fixed points of finite density quantum matter. Now, this is, of course, too broad and difficult a question, because we have very few tools to do this. But we do have one somewhat new tool, holography. And so, here I'll describe some new results that come just from studies of holography at finite density, motivated by this one. Now, if you're reductive and you think our goal should be to study classical and quantum gravity using strings, then I would say reductively you can just view this as an attempt to better understand what is clearly a rich zoo of black hole and black brane solutions in string theory and their dual physics. And in fact, it is really pictures like this that have motivated the exploration and understanding of this rich structure in the last few years. It's just, for most selfish purposes, learning about black holes has been greatly stimulated by this interface with condensed matter. So to talk about this well, I have to introduce the simplest cases of holography at finite charge density. So one of the minimal ingredients you need to ask questions about things like resistivity, well, finite temperature holographic matter is mapped in ADS-CFT to a charged black brane geometry. The Hawking temperature of the black brane generates the temperature. The charge is, if you want, the doping of the matter, the extra charges. And the simplest action that would support, at least from the bottom up, a holographic dictionary that would have a current whose conductivity we could compute, would then be that which supports ADS, an Einstein term with negative cosmological constants, and one Maxwell field, whose coupling I've said this way by convention. So the first place to start is asking what are the black hole and charged black hole solutions of this action. And these were found in the late 90s by Cameron and collaborators. So the simplest solution is the ADS analog of the Weismann-Nordstrom solution of flat space relativity. It has a line element that if we set the function f to 1, would just be anti-de Sitter space with curvature r, but there's this so-called embracketing factor f that tells you that depending on the charge and mass of the hole, there's a horizon, and there's a gauge field, an A naught, which tells you the charge of the black hole. The component which falls out more slowly than infinity is the chemical potential, and the response, or the charge density induced by that chemical potential, is the subleading curve. Now, in the case of a 4D bulk, dealing to a 2 plus 1 dimensional field theory, which is of interest in many cases, the extreme limit, which would be the ground state of the dope theory, the place we might expect to find quantum criticality if we're going to find it anywhere, has a near horizon geometry that looks like this, much simpler than this complicated metric. And in fact, if you stare at this for a second, you recognize that the x squared plus the y squared is just a metric on R2, and this is just a metric of ADS2. So the geometry in the near horizon is ADS2 times R2. Now, the failure of the R2 to shrink as you go towards the horizon means that the area of the black hole is not shrinking. There's a constant area, in fact, divergent area. And so there's an extensive downstate entropy. Whatever the zero temperature state is, it's very unusual. Now, there are known systems that would give an extensive downstate entropy. For instance, if you took a bunch of magnetic spins that were free about very weak interactions, then before the interaction energy is important, free spins certainly would have extensive downstate entropy. Phonons above the Debye temperature could have somewhat similar physics in many ways to this. But for a strongly coupled state of matter coming out of some strongly coupled field theory, this seems very exotic. So many people have suspected, as Andreas discussed, that this is probably a highly idealized model of what comes out in holography. of condensed matter theory of some technique, people found fascinating non-thermally liquid behavior that relies strongly on this ADS2 quantum critical region to get the various singular power law behaviors seen in two-point function. Now, I want to stress here that this fascinating behavior that's been seen is what I would call 1 over n fascinating behavior, in that there's a quantum critical theory here, which scales with the leading large n and takes most of the degrees of freedom, and the responses that are of so much interest, because they're non-thermally liquid like, are all sub-leading compared to that large n behavior. Okay, so this is in some sense a probe interacting with a very large background quantum critical theory. So the next question we might ask is, what happens if we start to make life a little more generic? Let's take John's advice and add parameters or add those fields and parameters and see if this result is robust. So let's take down the simplest toy actions that have more than just the Einstein field and the Maxwell field. So the simplest extension that you might think of, I think Gary will talk about the other simplest extension, which would be to add a charge scalar. We'll add a neutral scalar, the dilephone. So the Lagrangian you might write would be something like Einstein plus a kinetic term plus some gauge coupling that depends on the dilephone for the U1 field, and some potential, which I've separated out from the cosmological term. Now, very simple choices with just such an action, you will qualitatively union your horizon geometry for charged black brains to start to incorporate more and more of the things that condensed matter physicists talk about, so I'm going to go through them as illustrative cases. So what's the simplest case? Well, I wrote here the dilephone-dependent gauge coupling, that's why I'm calling it a dilephone. So let's just first set v to 0 and deal again. Well, in this case, you can actually find asymptotically ADS solutions where the horizon geometry is actually an exact solution of the equations of motion, and in externality, it takes this form. So instead of the ADS2 plus R2-like form, where dx squared plus dy squared is independent of r, here the spatial coordinates are indeed shrinking as you go to the horizon, and the coefficient with which they shrink is different from that in the temporal direction. There's a z that distinguishes the two. In addition, because we turn on a charge, we're studying charged black holes, the dilephone coupling here, in presence of a charge in F, sources some kind of near horizon potential for the dilephone. So there's an attacker mechanism the dilephone runs. Here it runs logarithmically near the horizon, and by bad choice of typing, I call that W, that should be R. So we find two new ingredients here. There's a dynamical critical exponent z that tells you how time and space rescale differently as you go towards the horizon. There's a scaling variance if you rescale time to the deep power of your spatial rescaling. And there's also some constant k governing how the dilephone is running. And the solution runs to either weak or strong coupling very near the horizon if you have electric or magnetic charges in the black hole with the conventions that I use. Now, physically, even in this very simple case, this simple metric, there's several interesting differences from the Weiser-Nordstrom geometry. Okay, first of all, because of this factor of r squared in front of r2, there's vanishing entropy density at z equals 0, which is a big plus. Now, the metric also still exhibits a scaling variance with some finite z. The near horizon geometry of ADS Weiser-Nordstrom, you might think you should recover when you take alpha here to 0. You do. Z scales like 1 over alpha, and an element z goes to infinity, and the metric you get is indeed one where time rescales, but space does not. Now, on the other hand, this whole solution doesn't really correspond to that of scale invariant fixed point because there's this pesky running scalar. Okay, so the dilephone breaks the scaling symmetry. If you want exactly scale invariant solutions with the same properties, you can find them as solutions of slightly different low energy theories, but I will not be interested in those today. And I should point out that my technique is not so different from what Andreas discussed. Even in these geometries, as opposed to ADS2, you can still obtain non-Fermi liquids, which have linear resistivity in their leading transport, by putting probe D-branes in the background of this metric and studying the transport of their terms, which was done by these authors. Okay, but again, the linear resistivity is not a prediction. There's a parameter, and you vary the parameter. You vary the response. So now let's enrich this scenario by adding back the potential via phi. Okay, clearly this would become a tedious exercise if I tried to write down solutions for arbitrary v, but something that turned out to be useful is to simply write solutions where v takes the simple scaling form itself very near the horizon, where the dominant term is just an exponential governed by some data. So we get two parameters now, alpha and the gauge coupling, and beta and the potential. And if this term dominates, you then find a more general class of homogeneous isotropic near horizon geometries, and now they're characterized by two critical exponents. One, the dynamical critical exponent that I already mentioned, and the second called the hyperscaling violation exponent that I think most of us were familiar with until about a year ago. So I'll call this beta. The resulting metrics have this form. Here you can think of this R variable as the one that in ADS would be 0 at the boundary and infinity at the horizon. And you see that the powers of R here are shifted from the ADS values both by the dynamical scaling and by this theta, which in fact makes the whole metric not of the Lifshitz type form, but conformal to it. So these metrics are not even scale invariant, they're conformal to metrics that have a scale invariance. And again, in all the cases that I've seen in the literature, they're supported by running scalar fields whose trajectory typically hits some extreme value, either very weak or very strong coupling for the U1 at the extreme horizon. This signals a breakdown of the low energy action that was used. We'll talk more about that as we go on. But before expanding on that breakdown, which indicates that these are most intermediate phases, let's describe the most interesting features of these geometries. So first of all, the free energy density, in the presence of hyperscaling violations, scales in different ways from what you get based on naive dimensional analysis, where there's a length scale based by the correlation length, and everything scales like the right power of that length scale. In the scale invariant field theory in these space dimensions, normally the free energy per unit volume is e to the d plus 1. But these metrics instead will have horizons, but if you go and compute the thermodynamic quantities the way Gibbons and Hawking taught you or whatever, you'll find the free energy per unit volume scales as e to the d plus 1 minus theta, where theta is the hyperscaling violation exponent. So in many respects, the thermodynamics of the dual theory is such that each effective space dimension to the d dimensions theta over d. They're really d minus theta effective states